So we're going to spend the next few minutes talking about the ozone layer and the ozone hole. And I want to start with the first misconception about the ozone hole. And that is somehow the ozone hole and global climate change are related and one causes the other. This is just simply not true. In fact, they're completely different, take place in different parts of our atmosphere, and they're not related at all. So that's why we didn't talk about the ozone hole in chapter 8 when we were talking about global climate change, but we talk about it here in air quality and air pollution. So, first of all, ozone. We already saw this as a criteria pollutant. It's three molecules of oxygen that are combined. And when we talked about it as a criteria pollutant, something that's regulated by the EPA, we said it's really bad for you. It can cause respiratory problems and plaque on your arteries. And while that's completely true, and we don't want ozone here in the troposphere where we live, we do want ozone up in the stratosphere. So if we look at this graph right here, we have altitude on the y-axis and ozone on the x-axis, and you can see that we want really, 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 really low amounts of ozone down here at the surface of the Earth. But northward, about 17 kilometers or so, up to about 30 kilometers, we want lots and lots and lots of ozone. So that's where you see this big stick out here, where there's lots of ozone, up to 25 millipascals in pressure. It's one of the ways we can measure ozone. And the reason that we want lots of ozone up in our upper atmosphere is it helps block some of those UV rays that are coming from the sun. And, it's summer right now, so we know we don't want lots of UV rays hitting us because it can cause sunburns, cause cancer, it can actually cause synthetics to break down, etc. So it's kind of like the sunblock or the first line of defense for us in the atmosphere. So a way to remember this is ozone, good up high, bad nearby. So if we look at a picture of the Earth and we look specifically at the thickness of ozone, and here we're measuring ozone in something called Dobson units. It's named for the person that discovered this measurement. You'll notice that where we have the thinnest amount of Dobson units, so the reds, the purples, and the blues are actually lower amounts of ozone than the greens, yellows, and oranges, you'll notice it's kind of really problematic here down above Antarctica. And we know this is Antarctica because if you look right there, that's Australia. So we know we're in the southern hemisphere. The giant landmass below Australia is Antarctica. So down in the South Pole, we noticed somewhere around the 1980s that there was a giant hole in ozone, or a very, very kind of circular thinning of ozone above Antarctica. And the question is, why all of a sudden do we have this thinning of ozone, and why is it specifically over Antarctica? And we're gonna get to that in just a minute. So if we look at kind of other models, other graphs, here we have total ozone in Dobson units versus time, and you'll notice that we weren't doing so bad. We had kind of good thickness of ozone and in the atmosphere in the southern hemisphere, and then somewhere around the 1980s, we saw this massive, massive decline of ozone. So what are the effects of ozone depletion? You get increased UVB radiation specifically. So there's different types of UV, UVA, UVB, UVC. Ozone hole or thinning of the ozone causes increased UVB rays to hit the surface. This can cause skin cancer, cataracts, damage to plants, to plankton, to fish. So some of our primary producers on Earth and in the ocean, which can cause a complete trophic cascade, mass extinction event if these species were to die because of UVB radiation. It also can break down synthetic polymers. So who's heard CFCs or chlorofluorocarbons? Well, chlorofluorocarbons are something that kind of we heard a lot of buzz around in the 1980s, 1990s. If you think of Aquanet hairspray or big aerosolizing hairspray, it kind of used to be, oh, that's what CFCs are. Well, what are these CFCs? Well, first of all, they are chlorofluorocarbons. So there are three different elements in this compound: chlorine, fluorine, and carbon. They are gases. They're non-toxic and inflammable, so they won't make you sick and they won't catch on fire. So they were discovered in 1928, and in the 1960s, they were widely produced and consumed. They were in just about everything because we thought we had found this miracle compound, something that's not poisonous, it's not going to catch on fire, it's not going to explode. So it was used in refrigerators and cars and machinery. It was cleaning agents, it was foaming agents for insulation, for packaging cushion. Anybody with a home that was built in the 1960s or after had CFCs as insulation in their home. All aerosol sprays at the time, just about, it seemed like, had CFCs in them. And that's where you sort of got this image of big hairspray aerosolizing products and CFCs. But in 1974, we actually discovered that CFCs could deplete the ozone. And by 1985, monitoring of the ozone hole over Antarctica was basically positive proof that, in fact, CFCs had started to destroy the ozone. So, why was it that if all our measurements between 1960 and 1980 had pretty good ozone? Well, the reality is this isn't something that happened overnight, right? You started to use the CFCs in the 60s, and they had to build up in the atmosphere, make its way down to the southern hemisphere, and actually destroy ozone. So in 1987, there was a meeting of several nations in Montreal, and the Montreal Protocol was adopted. And this was an agreement between many nations that said they would limit CFC use. And after 1987, there was actually the London Agreement, where nations got together this time in London and said they would just ban CFCs. In 1990, the United States actually modified the Clean Air Act to phase out the use of CFCs. So alternatives have come into place, things like halofluorocarbons. So this is halogen, fluorine, and carbon, phosphofluorocarbons, phosphorus, fluorine, and carbon, and sulfur fluoride, which is sulfur and fluorine. These were developed, however, they can contribute to CO2 in the atmosphere. They're also greenhouse gases, so it was kind of like we traded one issue for another. So first of all, how is ozone formed? Let's step back a second and think about, before we think about destroying ozone, how do we get all this ozone in the stratosphere? And the key about ozone in the stratosphere is it's formed completely different than ozone in the troposphere. So ozone down at ground level is actually formed when different compounds combine. In the stratosphere, it's formed by something called the Chapman cycle. And this is a diagram of the Chapman cycle. So we know we have plenty of molecular oxygen, O2, in the atmosphere. We know this because we are breathing. So we have all this O2 floating around. And light, so a photon is in energy of light, actually can split oxygen. We call this photolysis or light splitting. So sunlight will come and rip apart that oxygen molecule. And this creates two elements of oxygen. But oxygen, remember, is not a noble gas, right? It's not sitting in our group 8 on the periodic table. It's actually in group 6A, so it is not happy. And why is it not happy? Remember back to chapter 3. It's not happy because it only has 6 electrons on its outer shell instead of 8. So oxygen doesn't like to be by itself. So one of these little oxygens kind of floats around. It says, hey, I see some molecular oxygen hanging out in the atmosphere. I'm going to join that party because I don't like to be by myself. So molecular oxygen forms with elemental oxygen and creates ozone. And that's how ozone is created in the stratosphere. But remember that light is still emitting, so photolysis comes along and will split up ozone, and it'll take that ozone, it'll split it up into molecular oxygen, which will form with another free-floating oxygen, form ozone over and over and over again. Or sometimes ozone will see one of those free-floating oxygens that's floating around, one of those elemental oxygens, and it'll go and make two molecular oxygens. This step right here, where ozone forms with an elemental oxygen and forms two oxygens, is very, very, very slow. And this is important because in nature, ozone is created much more quickly than it's broken down. So while ozone is recycled, it's formed, it's destroyed in the atmosphere, it's formed more quickly, and as long as it's in homeostasis or equilibrium, we have plenty of ozone in our atmosphere. So, getting back to CFCs, why are we talking about CFCs? What makes them important, and why, remember, is the hole only over Antarctica? Why don't we see this everywhere in the atmosphere? Well, the answer is there's a very, very unique weather condition in Antarctica that happens there and no place else on Earth that makes it kind of a perfect storm, so to speak, for ozone destruction. So, the South Pole over Antarctica is the coldest place on Earth. And in the winter, you'll have temperatures down -80 degrees Celsius. And what you get too are these really, really strong circulating winds or polar vortex. And we heard a lot about the polar vortex last winter, I remember. But this is kind of a kind of Arctic tornado happening over Antarctica. And these really strong circulating winds in the middle and lower atmosphere actually will suck air from the upper atmosphere into this polar vortex. So you get a region of very, very, very cold air, extremely cold air. And on this air, you have tons and tons and tons of ice crystals. And this is important because remember, CFCs have been emitted into our atmosphere and they're kind of floating around everywhere. And through kind of natural chemical combinations, CFCs will form many, many different types of inactive chlorine. So you can have nitrite chloride, you can have um, hydrochloric acid, all different types of inactive chloride. And this inactive chlorine will actually sit and dance on the ice crystals and form many, many different types of reactions. Specifically, the inactive chlorine will kind of be on these ice crystals and form what we call activated chlorine or Cl2. And Cl2 is really important because this activated chlorine is not actually responsible for the destruction of ozone, but it's the first kind of step in making something that will destroy ozone. So it's kind of primed and ready to destroy ozone. So you have this happening in the winter in Antarctica, which incidentally is during our summer. So because in the southern hemisphere, they're going through their winter when we're having summer. And so let's say it's July in Antarctica, and you have all this inactive chlorine dancing on these ice crystals, forming all this active chlorine, Cl2. Well, in kind of August, September, when the sun finally rises, because if you've ever been to, say, Alaska in the winter, you might notice it's dark year round, or Alaska in the summer, it's light year round. Well, the opposite happens at the South Pole in Antarctica. So during the winter in Antarctica, it's dark pretty much 24 hours a day. So when the sun finally does rise, come August, September, you get that photolysis or that light splitting. And the light will actually split the activated chlorine or Cl2 and form two chlorine radicals. And we call it a chlorine radical because it's Cl minus, and it's the radicalized form of chlorine. And it's really important to notice that for every one inactive chlorine that we have that creates one active chlorine, we get two chlorine radicals. And the chlorine radical is what's responsible for the catalytic destruction of ozone. So let's think of that word, catalytic destruction. Catalytic. What is a catalyst? It's something that triggers a reaction. So the chlorine radical actually triggers the destruction of ozone, but it's not changed in the reaction. So this little chlorine radical, free chlorine, can destroy ozone go around and do it again. It's kind of like a bowling ball and a bunch of pins. So you take your bowling ball, you roll it down the alley, you destroy the pins, and you get your bowling ball back. And you can take it and you can keep kind of destroying those pins over and over and over again. And one little chlorine radical can destroy 10,000 ozone molecules in a single month. And remember, for every compound of inactive chlorine, which we get from every compound of CFC, we get 2 chlorine radicals. So very, very, very destructive. So ultimately, we started with our CFC. It became inactive chlorine in the atmosphere down in the South Pole during the really, really, really cold winter. It danced on an ice crystal and became active chlorine, or Cl2. Then UV light or photolysis happens. It breaks apart one of those chlorine radicals, and the chlorine radical can strike at the ozone. So what it will do is it will actually rip off one of the oxygens, and you'll get an oxygen molecule and chlorine monoxide, or chlorine complexed with oxygen. But this combination right here is not very strong. Both chlorine and oxygen form anions, so they don't like to combine because they're both negatively charged. So one of those free oxygens that's been floating around from the Chapman cycle, remember from photolysis that ripped apart the molecular oxygen, it's going to steal that oxygen from chlorine monoxide, because this oxygen-oxygen covalent bond is much, much stronger, much better of a bond. So then your oxygen molecule is going to kind of float off into the stratosphere, and your free chlorine will continue to go and find another ozone to deplete. I like to think of it as a toddler in a room full of Jenga sets. The free chlorine molecule is your toddler, and ozone is all of these Jenga sets that have been set up, or Lego towers, or whatever kind of an analogy you want to use there. And the toddler is just running around knocking over these Lego sets and these Jenga or Jenga towers. And if you were chasing after the toddler, they can destroy them much faster than you can rebuild those Jenga sets. And at the end of the day, that's what happens. The chlorine radical can destroy this ozone much, much faster than the Chapman cycle can rebuild it. So if we look at kind of when the ozone hole area is the largest, you'll notice that it's always the biggest when the sun comes out. So in spring, in Antarctica, which is our fall, between August and December, because you have all that photolysis taking that activated chlorine and creating the chlorine radical. Now, some good news. If we look at chlorofluorocarbons, this is specifically CFC11, also known as Freon 11. If we look at the levels over Cape Grim, Tasmania in the southern hemisphere, you'll notice that while CFC levels were increasing dramatically, they have since started to taper off and go down since we have banned CFCs. So finally, to summarize, to get the ingredients for the ozone hole over the Antarctic, you start with CFCs, which are also known as chlorofluorocarbons, or Freon. It becomes inactive chlorine in the atmosphere. This inactive chlorine is just kind of floating around in the atmosphere. If you go down to winter in Antarctica, you get that polar vortex. It's dark. It's really, really cold, so negative 80 degrees Celsius. You get ice crystals. These ice crystals actually form on something called a polar stratospheric cloud. So that's when we had that kind of air coming in from the upper atmosphere into the polar vortex. On these ice crystals, you have inactive chlorine turn into active chlorine, which is also known as Cl2. During spring, so come August, September, the sun rises, you get photolysis. So active chlorine, Cl2, will actually split from light into the chlorine radical, and then ozone is destroyed by the chlorine radical. And there you have it. Why we had an ozone hole, or still have an ozone hole over Antarctica, but why, for once, we've actually kind of been able to figure out, okay, A is causing B, so if we remove A, we can stop B. And we have seen the ozone hole actually repair itself as we have started to, as we have banned CFCs and other countries have phased them out or banned them as well. Unfortunately, we have no way of kind of pulling them out of the atmosphere. So, for the foreseeable future, we still have these chlorine radicals that can destroy ozone, specifically in the spring, but things are getting better.